All right, so welcome students. This is going to be the semester 1 review for Honors Chem. I'm re-recording this video because the recording feature on Zoom, for some reason or another, did not work very well. So we're going to re-record the entire thing here for you from beginning to end, looking at all the sample problems that we have provided for you on the review guide that was posted to Canvas. So here, we're going to go ahead and look at a lot of handouts. So you want to make sure that you have a couple of handouts handy for yourself today. You want to make sure you have the nomenclature guides, the electronegativity table, the solubility table, the polyatomic ion sheet, and the molecular geometry document that was provided in the Google Drive folder for you. And so with that, we're going to go ahead and get started here. We're just going to start looking at problems all the way through here. And so what we've got here in front of us is essentially a sample problem, and I'm just going to go ahead and work them through here, and I'm going to go ahead and try to do this as briefly and efficiently as I can. So please follow along as we go through, and let's begin. And so the very first problem here is going to be looking at significant figures. And so for the significant figures, what we want to be able to do is to go ahead and identify all of the sig figs. Remember, the rules here was that all non-zeros are going to be significant. And so here, with regards to that, what we'll do is we'll look at the number. And so we're going to take a look at the first number here at the very top, 29321. Each of these numbers are non-zeros, so each of these numbers is significant. And typically the question that you'll be asked is, how many significant figures are there? So here, if we count them all, that tells us here that we've got a sig fig count of 5 significant figures. Moving on to the next problem. Here we've got a total of 5 digits overall. Got a couple of zeros here in between the 1 and the 3, and then we've got a 0 at the end. Now, when we look at the rule is that all non-zeros are significant. So we can easily go in here and say that the 1 is significant and the 3 is significant. But when it comes to the zeros, zeros are only significant under a couple of circumstances. The first circumstance is when the zeros are between significant figures. So here, notice we've got a 1, we've got a 3. So these two zeros right here are going to be significant themselves because they're considered middle zeros. The zeros at the end are not significant unless there's a decimal. And so in this particular problem, there is no decimal in this number. So that 0 at the end does not count. If we go ahead and look at the total count here, we have a total count here of 4 significant figures. Looking at the last problem here, we've got 23.0. So easily, again, the very first rule, all non-zeros are significant. So that means here that the 2 and the 3 are significant. But the 0 here at the very end normally would not be significant, except there is a decimal here. So that 0 does count. And so the count here would be 3 significant figures. Now, the main thing to know with regards to each of these problems is that you're not necessarily going to be asked problems to identify how many sig figs there are in a number, but you will be asked to use these skills to identify how an answer from a calculation should be reported. So keep it in mind that when you do the calculations, you do not round until the very end, and that rounding is more of an accuracy reporting to the right number of significant figures. So with that, let's move on to the next section. So the next section here asks us to look at the pen, and so here's the first question that we're going to look at. So what's the pen count for each of these elements? And so for that, what we need to do is we need to have access to a couple of bits of information. A useful piece of information here is going to be a periodic table. So if you have that handy, go ahead and grab it. So I've gone ahead and put a periodic table over here on the far right. And so let me zoom in on this a little bit. And for us, what we need to be able to do is we need to be able to identify the atomic number for these particular atoms. And so we're going to begin with calcium. And I'll zoom in here on the periodic table that we've got. Notice here for the periodic table, right off the bat, we can tell, and I am using the periodic table of ions. If you're using the regular one, that'd be fine as well. But here, what we've got is an atomic number of 20. And so remember, for a neutral version of this particular atom, the proton and the electron count is the same. So if I'm doing a pen count here, the pen count here for the proton count is going to be 20. That's going to correspond to the atomic number. The electron count here is going to be 20 as well because this is a neutral atom. And then for the number of neutrons, what we're going to do is we're going to then look at the mass and subtract the number of protons. Now, I'm going to switch periodic tables here to give us a better view of the mass. So here is the mass of calcium. So notice the mass is 40. And so we're going to take that number, we're going to round it to the nearest whole number. That gives us 40. And then we're going to subtract the number of protons. And so that gives us here a total count of 20. So the numbers that we're interested here for the pen count are 20 for the protons, 20 for electrons, 20 for the neutrons. If we continue on here to the other couple of atoms here that we've got two of them. We've got neon. Let's go ahead and look at that atom. And so let me go ahead and get this information over here on the board for us. So notice here we've got neon. We've got an atomic number of 10, and then we've got a mass of 20. So when we look at the overall value here, we're going to go ahead and put that information here. And so the proton count here is going to be a 10 for neon. The electron count is 10. And the number of neutrons is going to be the mass, which is 20, minus the number of protons, which in this particular case is going to be 10. And so that'll give us 10 overall. So the numbers are 10 for the protons, 10 electrons, 10 neutrons. All right, and so for the last atom here, we've got iron. And so iron, if we go look for it on the periodic table, we got it over here. Notice it's got an atomic number of 26, and it's got a mass of 55.845. So we do the math here. Let's go ahead and use this color here. The proton count is equal to the number of the atomic number, which is the proton count, which is 26. The electron count is the same because it is a neutral atom. And then the number of neutrons here is going to be the 55.8, I'll just write it all out here, 55.845 minus the number of protons. Now, we want to make sure that we take this number here, the 55.845, we've got to round that to the nearest whole number. And so if I do that, if I take this out, this actual number rounds up to a 26. And so the answer here would be 26 minus the 26. And so that's the part that we want to make sure that we do. I'm going to go ahead and write this a little bit cleaner here. Minus the 26. And actually, that is not a 26 there. That is a 56. And so I'll write that there. And then that'll give us a total of 30 for this one here. And if I go back and put this in blue, the numbers here is 26 for the proton, 26 for the electrons, and 30 here for the number of neutrons. All right, for the next section, we're going to go and talk about average atomic mass. So when we're dealing with the average atomic mass, there is a pattern that you want to use in terms of the calculation. That pattern is the following. You want to look at all of the isotopes, and you're going to take the mass of the isotope, and you're going to multiply that by the percent abundance. And you do that for every single isotope that exists, and then you're going to get what we call a weighted mass, and that's going to be a number at the very end. And you're going to do this for every single isotope that is in the problem. So here, we look at this particular problem here. Here is a sample, and if you look at this here, we have a isotope. We want to know what the average atomic mass is of an unknown compound. It's got two stable isotopes. And the mass of the first one is here, the percent abundance is here, mass of the second, and the percent abundance. And so let's go ahead and do this out fairly quickly here. We're going to take the pattern here. Again, I already wrote it once, but let's write it again. We're going to take the mass, and we're going to multiply this by the percent abundance. The only thing to note here is when we calculate this percent, remember that it has to be in decimal form. So we're going to have to convert the 45% here to a decimal, and the 55% here to a decimal as well. So let's go ahead and do the math here. We'll take the mass of the first isotope, that's 87. So I'll write here 87 AMUs. And we're going to multiply that by the percent abundance, which is 55. If it's a 55 divided by 100, that'll be 0.55. And so that'll be 0.55. That'll give us a number. We'll calculate that number in a second. And then we'll do the other one, which is the mass of 56. And so we'll do 56 AMUs, multiply that by the percentage in decimal form. In this case, the 45 gives us 0.45 when you divide the 45 by 100. And so that'll be that. And then that'll give us a value too. So when we do the math here, overall, the values that we get are 47.85 at the very top, and then 25.2 at the bottom. Now what we're going to do at this point is we're going to take these numbers here and we are literally going to add them together. And when we do, the final value that we get is 73.05. And this is going to be AMUs at the very end, but this number here is the average atomic mass for this particular example. You'll repeat the process for all the other atoms that you've got that you're being asked to solve for, but remember the process here. Take the mass, multiply by the percent abundance in decimal form, add the weighted masses. The total is going to be your average that you're looking for. Now, if they're asking you to identify the identity, you go look at the periodic table and look at this mass, and then the mass or the atomic mass that's on the periodic table that's close to this value here but does not go past it, and then you look at the symbol that would be the identity of that particular element. Another concept that you're going to be asked to do on the exam perhaps is going to be identification of molar mass. And we've got a couple of compounds here that we're going to be looking up the molar mass for. AlBr3, HNO3, MgCl2. And so you're going to need a periodic table for this, so it's important that you grab that. And I'm going to go ahead and grab mine, move everything to the side here, and I'll do the work here on the right-hand side. And so let's go ahead and bring our periodic table up. All right, so I've got my periodic table up, and you want to make sure that you have yours handy when you're doing that. So go ahead and pause the video. If you need to, grab your periodic table of ion and your periodic table with masses, and then use that as we go forward here. I'm not always going to show mine on screen, so it's important that you have yours handy. So here we're going to need a couple of atoms. The masses, we need the mass for aluminum, and we need the mass for bromine. And so if I come over here to the periodic table, we look for the mass of aluminum. Notice the mass of aluminum here is 26.982, and the mass of bromine is 79.904. So let's go ahead and do that. For the sake of simplicity here, I'm going to go ahead and take this and I'm going to round these numbers to whole numbers for the sake of it. But if you're asking you for accurate answers, then you definitely do not want to round anything at all. But let's go ahead and do this. So what I'll do is let me minimize this and we'll come back into it. And so here for the aluminum, the mass of aluminum, we just found it to be 26.9. I'm going to go ahead and round that to a 27. And each of the bromine here is going to be a 79.9. I'm going to round it to an 80. So if I set this up, I essentially want the mass of an aluminum atom. I'm going to add that to 3 copies of the bromine. Now, I could rewrite this part as saying 3 copies of bromine. And I'm going to add that to aluminum. And all I have to do at this point is just replace the masses. Aluminum, I know now, is going to have a mass of 27. I'm going to add this to 3 times the mass of bromine, which is 80. And if I add all of these together, do the math, plug it all into the calculator, the total mass that you end up here is 267 grams. And this is going to be per mole of AlBr3. And so this here is your molar mass for this particular compound. Okay. Moving on to the others, let me minimize the text here. So let's continue on, and we'll do the next problem here. The mass of hydrogen, we're going to assume it's a mass of 1, even though it's a 1.008. The nitrogen can be rounded to a mass of 14. Oxygen has a mass of 15.99, but I'm going to go ahead and put 16. Notice that there are 3 copies of oxygen. So if I'm looking for the molar mass, I want to go ahead and put here, take the mass of hydrogen, take the mass of 1 nitrogen, and then take the mass of 3 separate oxygens. I can rewrite the oxygens as 3 times the mass of oxygen, and I'm going to go ahead and add that to the nitrogen, add that to the hydrogen. So here, replacing the symbols with the actual mass, I'm going to wind up getting here a 1, plus for the nitrogen, it'll be a 14, and then plus 3 times the oxygen. Oxygen is 3 times 16. And so go ahead and evaluate all of these. Go ahead and take the 16 times 3. Take that total, add it to 14, add it to 1. And the total that you're going to wind up getting here is going to be equal to 63. All right? And so we'll write that as 63 grams per mole of HNO3. And so this here is your actual molar mass for this specific compound. Now finally, the last problem here, we got MgCl2 right here at the bottom. So let's go look up the masses, look on your periodic table. What we know for the magnesium, we know that the magnesium actually has a mass, and let me use a slightly different color here. Let's go ahead and use this color here. And so the mass of magnesium is 24.3 grams per mole. And then the chlorine is 35.453. Notice that there are two. So if I do this, what I'm really doing here is I'm looking at the mass of magnesium plus the mass of 2 chlorine atoms. The 2 chlorine atoms can be written as 2 times the mass of chlorine, and I'll add that to the magnesium. And all I need to do now is replace the mass here when I see the symbol. So what I'll do is go ahead and put it in here, and I'll put 24.3, and I'm going to add this to 2 times the mass of 35.453. If you go ahead and do all of that, plug it into the calculator, take 35 times 2, add it to 24.3, the total mass that you end up getting here is 95.206 grams per mole, and this is going to be of MgCl2. All right, so let's move on to the next topic of discussion here. The next topic allows us to look at Bohr diagrams. And so for Bohr diagrams, what you need to remember is the general construct is that at the center of the Bohr diagram, you're going to have the number of protons identified, you're going to have the number of neutrons identified, and then you're going to have concentric circles around which you're going to be adding electrons, and those electrons are going to show up as dots. Okay, so this is the general format. Remember that the maximum number of electrons that you're going to place here, so the max number of electrons is identified by the equation 2n squared, where n is the orbital number. Okay, so remember that from your notes. And so let's go and see how we actually draw this. So let's go over here to the problem. Here we've got one problem that we're going to look at. We're going to be drawing the Bohr diagram for the atom of magnesium. And so we had already looked at magnesium before. Let's go ahead and bring the periodic table back over here. And so we've got a periodic table here. And if we look at magnesium, magnesium happens to be in the 3rd orbital, and it's got an atomic number of 12, and it's got a mass number of 24. So we're going to use this information here to calculate the pen really quick, because you're going to need that. So let's go ahead and move everything out of the way so we can actually do the problem. So here we go. We know that magnesium is going to have a pen count of 12, 12, and 12. And so here we go. We're going to put the proton number in the center. So it'll be proton 12. We're going to take the neutron number, N12, in the center. And then we're going to draw a couple of orbits. Let's start with 1. And then we'll immediately place the number of electrons. 2n squared, that means in the first orbital you can put 2 electrons. That means we have a total of 10 remaining, so we'll do a second ring. In the second orbital, we've got 2n squared. N is 2, so 2 squared is 4, times 2 is 8. So we can actually put a total of 8 electrons. That'll be 1, 2, 3, 4, 5, 6, 7, 8. So that's 2 for the first orbital, 8 for the second. That gives us a total of 10. That means we are going to need one more orbital. I'll add that orbital here, and then I will put one at the top and one at the bottom, just so that we identify this electron here is a valence electron because it's in the outer ring, and the other valence electron is the one at the very top. Now in this particular problem, we were asked to draw a Bohr diagram, but what if we were asked to go the opposite way? From a Bohr diagram, could you identify the proton, electron, and neutron count? And here the very answer is simply yes, you can. And so this is what I mean. If this diagram is the only thing that you were provided and you were asked the question at the bottom here, you can see, let me move up. And so let's say that you were asked this question here: how do you find the number of protons, electrons, neutrons, and the mass number from this Bohr diagram? And so the answer is pretty simple. For the protons, all you need to do is look at the center. If the protons are identified here, that you're going to tell you protons is equal to 12. So that's how you can easily identify P12. The number of electrons is the same way, but except here, you're not going to look at the center. You're going to look at the circles, the dots, that represent electrons on each of the rings. So here you would count them. You have 1, 2. Second orbital, you've got 3, 4, 5, 6, 7, 8, 9, 10, and then in the third orbital, 11, 12, and that's how we identify that there are 12 electrons. For the neutrons, you would simply count the number provided in the center, N12, so that means that we have 12 neutrons. Now, what about the mass number? Well, for the mass number, remember that the mass number is going to be the total mass, and so that mass is going to be the combination of the mass for the proton, the electron, and the neutron, but we know that the electrons have a very small mass overall. So largely, the mass that's going to be associated here for a mass number is going to be related specifically to the number of neutrons and the number of protons. So if I want to add up the number there for each of those, then I would be able to get the total mass. And so in this particular case, the protons is 12 and the neutrons is 12. If I add those together, that'll give me a mass number of 24. All right, so now we turn our attention to the Lewis dot structures. And so here we have the next question right in front of us. We want to be able to draw the Lewis dot structures for the following compounds. Now I'm going to go ahead and, for the following compounds at the bottom, and we've got a couple of atoms. I'm going to go ahead and begin with placing the Lewis dot structure for magnesium here, just to review a couple of items. All right, so here we've got the Bohr diagram for magnesium. And we know that it's magnesium because the number of protons is 12. And we also can count the electrons, and we know there's a total of 12 electrons here. So this would be a neutral atom of magnesium. Now, what we're going to do here for the Lewis dot structures is where we're going to show you here with the example of magnesium. For a Lewis dot structure, all we really need to do is take the initial items here in the center, and since we now know that it's magnesium, what we're going to do is we're going to replace that with the symbol Mg. And then we do not need any of the core electrons, so we're going to go ahead and remove those from the mix here. And so I'll do that here. Don't need any of these, so I'm going to take those all out. And I also do not need the electrons in the center, so I'll take all of those out. And we're going to be left with a symbol. Now, these electrons that remain are the valence electrons. These were the electrons on the outer ring. And so to finish off the thought here, we're going to take the ring off. We're not interested in the ring at all. And we're not interested in that ring there. And then what we'll do at this point is we're going to bring these electrons here. And then we're going to bring them in. And so I think maybe the best thing to do here is to erase and then just replace. And so we're going to need a Lewis valence electron at the top. And then we're going to need over here at the bottom, we're going to need the other one. So here is the Lewis dot structure for magnesium. So we need to make sure that we identify the valence electrons. Now the easiest thing here for me to do so I can double up on concept is to do the electron configuration for each of these atoms here as a way to build everything. So let's go ahead and do that now. All right, so let's begin with the very first atom. We're going to start with lithium, and let's go look at the electron configuration. Now, there are certain ways that you can actually do the configuration from the periodic table, so it would be very helpful if you take a look at the periodic table and follow along with me. So let's go ahead and bring our periodic table to the screen. All right, so what we've got here is we've got a lithium atom, and so that lithium atom is located right here. Remember that there was a couple of divisions here for the periodic table, so let me go ahead and put those on the screen right away for us. So here is the information that you need to be aware of. So remember, the first two columns are S type of electrons in the S suborbital. The elements here in group 3 to 12 are in the D suborbital. Elements group 13 through 18 are in the P orbital, except for helium. Helium is an S orbital. Elements down here, the lanthanides and the actinides, these are suborbital F. And so when we look at this diagram here and we try to figure out what's the Lewis dot structure for lithium, it's important that we can identify the configuration. And that's what I want to identify for you first. And so when you look at this here, we want to get to lithium, but we want to make sure that we go across. So notice in the first orbital, we've got an S electron, and then we've got another S electron, which is the helium. So that'll be 1s2. And then in the second orbital, it's in the first position, so that'll be 2s1. So when we look at the configuration here for lithium, the configuration here should be 1s2, 2s1. And it's this particular configuration then that we have to pay very close attention to. We want to look at the highest orbital. So these numbers here, 1 and 2, are respectively here as 1 and 2. So 2 is the biggest orbital, or the outer ring. There is a S suborbital type of electron, and there is one electron. So that one represents the number of valence. And so this electron here is your valence electron count. So lithium is going to have one valence electron. And so when we actually do that, when we're drawing the Lewis dot structure, we always begin with the actual symbol, Li. And then since we've got only one valence electron, that means one dot. And so we would draw the structure for lithium as such. So here is your Lewis dot structure for lithium. If we look at the structure for magnesium, notice magnesium here is in the third orbital in the second position. So it's going to end in 3s2, but that means that all the other positions are going to be filled. And so the final configuration should look like the following. And so here is the configuration for us. We notice here 1s2 is because in the first orbital there's s, and the second s over here by the helium. The second orbital, you've got two s's. That'll give you a 2 exponent here. And then we go across into the p section of the second orbital, and there's 6 total. And so that gives us the 2p6. And then we go to the third orbital, 3s1, 3s2, and that's the ending here. So the highest orbital, if you're looking at the periodic table, is a 3, and that is actually identified right here. So when we look at the exponent, the number 2 designates the number of valence electrons. So I'm going to go ahead and circle that. That there is your valence electron count for magnesium, and that means that if we draw the Lewis dot structure here for magnesium, we have to begin with the symbol, and then we always draw in the dots that are represented by the number of valence electrons. Since we've only got 2, we're going to draw 2 dots, one at the top and one at the bottom. You could have, if you wanted to, you could have drawn magnesium this other way with the 2 dots, one on the left and one on the right. Both of those are acceptable versions. So you could have definitely drawn that as well. Okay, let's go ahead and move on to the next atom. I'm going to clear up the board a bit. All right, so as we turn our attention now to iron, iron is located right here, number 25. It is in the fourth orbital, but notice that it's inside the D subgroup. So remember, when we ever look at the D subgroup, the orbital count is going to be n minus 1. So in this case, the orbital is 4, 4 minus 1. When we get to the D group here, you're going to have to write 3D, and it'll be 1, 2, 3, 4, 5, 6 as the ending position. So let me go ahead and write the configuration fully on the screen, and then we'll identify the Lewis dot structure. So we've got the full configuration here for iron, and notice here 1s2 is because in the first orbital we've got 1, 2 positions, 2s2, second orbital 1, 2, 2p6, that means second orbital all the way across, all of these are filled, and there's a total of 6. 3s2 brings us right here, 3s1, 3s2, 3p6, if we continue on, that's third orbital in the p group, and there's a total of 6. 4s2 right here, 4s1, 4s2, and then 4 minus 1 is 3, 3d, that means 3d1 all the way to 6 right here. Another way to figure this out is if we add up the exponents here, all of these exponents should equal to the atomic number of iron. So now that we've got this, we've got to figure out what is the highest orbital number. So the easiest way to figure this out is, we know that this is going to be a 3 because it's 4 minus 1, so we keep going all the way to the right, and so the highest orbital number is going to be 4. And if you look at that, that 4 is right here, and there is a total of 2 electrons here. And so when we come in here, the valence electron count is actually a 2. And I've already put a circle around that right there. And so when we do the electron configuration for iron, in this particular example, we're going to write down the orbital number, or excuse me, the symbol, and then we're going to have 2 dots, one top, one bottom. And so this here is your Lewis dot structure for iron. Let's turn our attention to a couple of compounds. How do you figure out the Lewis dot structure for compounds? Well, you'll have to get the Lewis dot structure for individual atoms, and then you can join them together, and that often helps you identify what kind of bond it is and the type of compound. Okay, so let's begin with this compound here, NaCl. We know that sodium is going to be in group 1, so it'll have one valence electron, and so we can draw sodium like so, Na, with a dot. Normally we put the dot at the top, but I'm going to go ahead and put the dot over here on the right-hand side. The other compound is chlorine, or the other element is chlorine. Chlorine is right over here. Notice another way that we can find valence electron counts is we can go from chlorine, go to the very top, and notice we've got group 17. 17 minus 10 means that you should have 7 valence electrons. So for chlorine, we should be able to go chlorine, and then we'll put the electrons. I'm going to put them in blue. That'll be 1, 2, 3, 4, 5, 6, 7. And so notice here we've got a bond. I'm going to just denote that bond by making sure I put a little dot there to distinguish that. But notice that bond there. Because we have a metal and a non-metal, this particular bond is known as an ionic bond. And as a result, this entire compound is known as an ionic compound. So this is the way you would get the Lewis dot structure for the compound. The only thing to remember here when you're dealing with Lewis dot structures of compounds is you have to make sure that every single atom has the right number of electrons to equal an octet. So chlorine has 8 electrons because the electron here from sodium was lost, so it belongs to chlorine. That means you've got 2, 4, 6, 8, so the chlorine atom has an octet. And since the sodium was able to lose the electron, that means it lost the electron here. That means it would have 2 in the 2s orbital, 6 in the 2p orbital, giving you an octet, so sodium would be okay as well. Finally, let's look at the Lewis dot structure for lithium chloride. All right, so with lithium, we know lithium here is in group 1, so we can easily do the same thing that we did for the sodium before. We can write here Li, and it's going to have 1 dot. I'm going to put the dot on the right-hand side for convenience sake. And then we've got chlorine. We've already established that chlorine is going to have 7, so I can go ahead and come in here, put a dot, and then I'll put the chlorine, and then I'll give it its other 6. So it'll be 1, 2, 3, 4, 5, 6. Again, the bond exists between the lithium and the chlorine. We can see that right here. Because we have a metal and a non-metal, we definitely know that this particular bond right here between the two atoms is an ionic bond that makes this entire compound an ionic compound. So let's move on here. We're going to look at the next section. We're dealing with valence electrons, but in particular, how do you find valence electrons from the periodic table? So you definitely want to be able to do this. So let me bring up a periodic table copy here, and I'll show you a very quick way to figure this out. All right, so here we've got the periodic table. We've got only the parts that are relevant. What is important here, if you're going to use the valence count, you can really count on a couple of groups. Any element in group 1 is typically going to have a +1 charge. That means that it will have 1 valence electron to give. So this particular group here is going to have 1 valence electron. And that will include any element in this first group. In the second column, this entire column here, these elements typically have a +2 charge, and that's because they're going to have 2 valence electrons. If they lose these electrons, this is what gives them a +2 charge overall. I'll do the same thing here for the group 1. Typically, it gives us a +1. Now, if you look at the periodic table of ions, you'll see that all of these elements here, the transition, they may have more than 1 charge, so they're not very dependable as to what charge they'll have. You'll have to reference that document. But we do know that we can use a similar technique over here when it comes to elements in groups 13 through 18 by looking at the group numbers. And so here is the process here. Specifically, if I take the group number, if I take 13 here, show you the math up top, if I take the group number here of group 13 and I subtract 10 from it, why 10? We're subtracting the elements here, or the electrons are in the D group, and then that'll give us a total count of 3 valence electrons for that very first one. So this group 13 has 3 valence electrons. If we do the same process here for group 14, that'll be 4 valence electrons. And in group 15, that'll be 5 valence electrons. Group 16 is 6 valence electrons. And if we're looking at group 17 here, this is 7 valence electrons. And group 18 is 8 valence electrons. The only thing to distinguish here is in group 8, the main thing to remember is that these elements here, group 18, these elements here are known as noble gases. And since they have 8 valence electrons, that is your octet, which is what we're looking for overall. So this is the way you tell the number of valence electrons, by looking at the periodic table. You often want to do this when you're trying to figure out valence electrons very quickly and do not want to go to the electron configuration. But if you want to go and do that, you can definitely look at the previous problems we've done where I showed you how to do that. Now, for the sake of argument, what we're going to do here is we're going to look at the couple of other atoms and we're going to be developing the electron configuration. And in that exercise, I'll show you how to get the valence electron count one more time. So let's take a look at that problem. All right, so let's take a look at electron configuration, and here is the actual problem that we've got. We've got a couple of problems that we're going to work through, and we want to figure out the electron configuration for iron, sodium, oxygen, and neon. And so I'm not going to show the periodic table on screen, but you should be able to go through here and identify the configuration as I work through the problem. So here, the iron, and just for reference, I will show you the periodic table, but I'm not going to go through the detailed explanation that I've done before. So notice here you've got the iron. Iron is in group, it's in the row 4, but it's in the D group. And so when we do that, we want to make sure that we identify the orbital number here is 4 minus 1, and it ends in the 1, 2, 3, 4, 5, 6. So it ends actually in 3d6. Now, previously we did identify this in the previous problem, but we have to go through the entire thing here, row by row or orbit by orbit, and making sure we identify the electrons based on the categories. So in the first orbital here, we're going to get a 1s2, 2s2, 2p6. Now, here we're getting the 1s from here, first orbital. There's only s electrons. In the second orbital, we've got s electrons here, and on the other side, we've got p electrons, and they're full. 2 and 6 respectively. When we go to the third orbital, we're going to get s electrons and then 3p6 as well. So here we get a 3s2 and a 3p6. So up to that point brings us up to the very end. We have to go to the fourth orbital, and there's a 4s2. So I'm going to make a little bit of room here for us and move this back a little bit. And this would here would be 4s2 and the 3d6. So this entire thing here, this configuration is the configuration for the iron. Now, since we're here, how do you identify the valence electron? You look for the highest orbital, looking at the coefficients. The biggest coefficient that we have among all of these is going to be the 4. That corresponds to the fourth orbital, and there are 2 electrons. And so I will circle the valence electrons here. In this particular case, there are 2 right there. All right, so let's go ahead and do the next one. The next atom here that we've got is sodium. Sodium is actually in group orbital 3 in the very first column. That's an s group, so 3s1 is where it stops. So I'm going to go ahead and put 3s1 here. And we have to go through the entire sequence. That means that every single suborbital before it is full. We begin at the first orbital, 1s2, 2s2, 2p6. And if I look at all these exponents here, and let's go ahead and change the color here. If I change all these exponents, 2 plus 2 is 4, plus 6 is 10, plus the 1 is 11, that should equal the atomic number of 11. And so this is the configuration for sodium. For oxygen, oxygen is located right over here. It's in the second orbital. Second orbital in the p group, 2p1, 2, 3, 4. So it ends in 2p4. And so let's go ahead and get that configuration here. That'll be 2p4. And if we go down the beginning, there'll be 1s1, 1s2, so we'll write that down, 1s2. Second orbital, we're going to go through the p's, so it'll be 2s, excuse me, not the p's, but the s's, 2s2. And then we're going to go across from the s's to the p's, so it'll be 2p, all of these are 1, 2, 3, 4, and so that'll be the other one that we've got here. So what we'll do is we'll bring this one over right there. And so if you count the exponents here, 2 plus 2 is 4, plus 4 is 8. That should equal the atomic number for oxygen. Since we're here, let's take a look at the valence electrons. We look at the numbers here, the 1, the 2, and the 2. The biggest number is the 2, and we've got 2 types. 2 electrons are in the s suborbital, and 4 electrons are in the p suborbital, for a total of 6. And so let me circle those in red. So these are a total of 6 valence electrons for oxygen. And then finally here, the last atom that we're going to look at is neon. Neon is a noble gas. It is in the group 18, and it's going to stop its configuration on 2p, 1, 2, 3, 4, 5, 6, 2p6. So it's very similar to oxygen's, except we're going to have 2 more electrons. And so that full configuration should be the following: 1s2, 2s2, 2p6. The unique and distinguishing thing about neon is that it's got 2 electrons in the s suborbital of the second orbital, and 6 electrons in the p suborbital of the second orbital. That means if I look at these valence electrons, which are going to be 2 and 6, if I add these together, these two is what gives me an octet. And so that's why neon is a noble gas, because it actually has this outer orbital, the second orbital, full in both the s and in the p suborbitals. All right, let's move on to the next topic. The next topic deals with identifying the charge of an atom. This is a skill that you need to know, and I will provide you a good way to figure this out. I had already shared it before with the group numbers above using the periodic table. I'm just going to go ahead and write those general trends that I shared before here on the screen, and then you can use them accordingly. We had previously identified that any element in group 1 is typically going to have one valence electron, and if it were to lose that electron, it would have a charge of a +1. Any element in group 2 would have a similar trend, but here it would have 2 valence electrons, and if it loses those valence electrons, it would have a charge of a +2. On the other side, however, when you're dealing with some of the anions, the negatively charged ions, the charges that we saw there was that if you were in group 17, if it were to gain the valence electrons, because normally these are going to have 7 valence electrons, and that would be neutral for these groups, but if it were to gain that additional 1 valence electron overall that it's gained, then here this would be a charge of a -1 charge. And then the group 16 would have a charge of a -2 for a very similar reason. It would then be able to gain the 2 missing pieces of valence electron to establish octet, and then it would have a -2. And then you can also go and extend this to group 15, which would have a -3 charge. Now, it's important to note here for the 3 groups here, 17, 16, and 15, this only applies to the negative, or to the atoms that are going to be non-metals. If you have a metal in these groups, then that would be a positive charge, because those metals are going to be able to donate electrons. Now, let's use this information here to figure out the charge of various atoms that we've got here. So we've got a couple of examples here. Let me show you the problem. The problem is right here. Can you identify the charge of an atom within the compound? And we've got a couple of formulas here. So if I use this as a guide, put this everything back here. And so we're going to use this as a guide. We know that a couple of atoms are going to be identified here. So we know that magnesium is actually in group 2. So magnesium will have a +2 charge. And so we can actually come in here and separate things out. Remember that each compound, the first atom is always the positive. So I'm going to go ahead and underline it and tell you it's positive here. And since we already know that it's going to be in group 2, it'll have a +2 charge. And so we'll say here +2 charge. Now, what's the charge of the chlorine atom? Well, notice here the chlorine atom is actually in group 17, so it'll have a -1, but that's only going to be for 1 copy. There are 2 copies here. And so in this particular case, each individual atom is going to be a -1, but because we have a total of 2 of them, that means -1 times 2 gives us a total charge of a -2. What that really means here is the total charge is a -2, the total charge of the magnesium is a +2, and if I were to add these together, the total charge is 0, and which is what we want, because this designates that this is a neutral compound. So when you're trying to figure out the charges of individual atoms, make sure you double check that the total charge equals 0. The second compound here is CrBrO3. Now we'll do the same process here. We're going to go ahead and identify the first atom. So we're going to break it right here. We're going to say that this atom here is a positive. We don't know what the actual number is, but we can use a number of tricks to help us out. We can go and look up the periodic table of ions and notice that here we've got 1, 2 elements in the anion portion. And so what does that mean? That means that all of this here goes together, and this is the negative, which means that this part here is the anion. And since we have 2 separate elements in the anion, that means that this is a polyatomic anion. So you can definitely go look it up on the periodic table of ions. And in fact, that's what I'm going to do. I'm going to bring up the periodic table of ions. And then show you where we can find this. Since it's a polyatomic, I'm going to look at the polyatomic section.